Good morning. I welcome you all in this session of fluid mechanics. Last class, if you recall, we were discussing about the manometers. The manometer is a device which measures the pressure of a system in terms of its difference from the atmospheric pressure or the pressure difference between 2 points, whether the fluid is at rest or fluid is in motion. And at last we discussed how the manometer registers the pressure difference between 2 points when the fluid is flowing through a pipe. Let us recall this again, that if we recall, this is like that if there is a pipe where the fluid is flowing in this direction, this is the flow direction, then if the 2 points A and B are connected, if the pressure PA is greater than PB, then the difference of pressure is measured by connecting a manometer, which is essentially a U tube like this, and we use a manometric fluid which is having a density higher than that of the working fluid, that is the fluid flowing through this pipe, and we registered this is the fluid, a deflection, that means the interface, that means the separation surface between the working fluid and the manometric fluid, the interfaces stand like that, and this is known as this is Y. And if we take the manometric fluid density is rho m and the density of working fluid is rho w, we have found that the delta P, that is equal to PA minus PB, becomes equal to rho m minus rho w g into y. That means, observing this deflection, manometer deflection, that means the difference in level of the meniscus y, we can find out the pressure difference. How to find it? By writing the manometric equation. That means we take this PQ line as the same horizontal line in this same expanse of fluid, which is the manometric fluid, and then what we do, we write the pressure here, equate the pressure here from this limb and equate the pressure here from this limb and find out this equation. Now what we started, that what is the situation, we see a very interesting thing, that when the fluid flows through an inclined pipe, let the flow direction is like this, the fluid flows through an inclined pipe where we are interested to measure the pressure difference between these 2 points A and B. And let us connect the manometer like this, a U tube like this. Let us connect an U tube like this, U tube manometer, and then what we do, then the manometric fluid will be having a deflection, definitely like this. Let us have a deflection of the manometric fluid. So we just, this is the working fluid, this is the working fluid. Let this deflection as it is, we call it as Y. Let from B, this distance is X, and A and B, there is a difference in vertical height between the section A and B, let it be delta Z, just I give this nomenclature delta Z. Now from simple manometric equation, that means if you take this line as the PQ horizontal line, and if we equate the pressure from both the limbs, now from this limb, if we come from this limb here first, PA plus, if the working fluid density is rho W, the same nomenclature, and rho m is the density of the manometric fluid, that means rho W delta Z plus X, that means rho W into G into delta Z plus X, that means this is the pressure of this column of liquid, plus rho m into Y. Y is the deflection, this is Y, this is Y. So this becomes equal to what? PB, that means the same pressure is here at the same horizontal level within the same expanse of fluid. So this is PB plus this pressure due to working fluid of height this, x plus y. that means rho Wg x plus y. So, if we equate this, we will see Pa minus Pb. So, rho Wgx cancels from both the sides, Pa minus Pb, so plus rho W G delta Z is equal to rho m minus rho W into G into Y. So, therefore, we see that if we compare these two equations, we see that from the deflection Y, manometer deflection, that means the difference in level of the meniscus, if I equate this rho m minus rho W into Gy, this gives an additional term from the pressure difference rho W G delta Z. In case of a horizontal pipe, A and B at the same horizontal level, so delta Z is 0, so we can put delta Z 0, this as a special case becomes this. But what is the physical interpretation of this term actually? Now, if I express the vertical elevation of A and B, this we will come afterwards in our studies, in our course, and Z2 from a reference datum, from any reference datum, if I just specify the elevation of A as Z1 and elevation of B as Z2, then I can write this as PA plus rho W G Z1, this quantity minus PB plus rho W G Z2 is equal to this one, rho m minus rho W, this one will come like that. So, therefore, we see this manometer deflection multiplied by the difference of density into acceleration due to gravity gives the difference of static pressure plus some term which is rho G Z1, where Z1 is the elevation of that point from a reference datum. So, this term is known as P star, that is piezometric pressure. That is, piezometric pressure is defined the static pressure plus the equivalent pressure corresponding to its vertical elevation from a reference datum. So, this is a very important definition which we will come across afterwards, piezometric pressure. So, always piezometric pressure is defined as static pressure plus the pressure equivalent of its elevation from a fixed datum, rho g. So, therefore, it registers a piezometric pressure difference Pa star minus Pb star. That means the same equation we can use for an inclined pipe, where if we find this quantity, this will give you the piezometric pressure difference instead of static pressure difference. So, if you will have to find out the static pressure difference, of course, you will have to deduct this thing. But sometimes directly we want the piezometric pressure difference. In that case, the manometer reading, from the manometer reading Y, we can straight away find out the piezometric pressure difference. In case of an horizontal pipe, the piezometric pressure difference become equal to the static pressure difference because delta Z is 0. All right. Now, next we come to the next part, that here we see that basically the pressure difference between 2 points in a fluid flow is measured by a manometer basically by this equation. Either it is a static pressure difference or it is a piezometric pressure difference, depending upon whether the pipe is horizontal or inclined. Now, if we want to measure a very small pressure difference, then what we have? We should have a substantial value of Y for a small pressure difference. In other words, you can say if we want to increase the sensitivity of the manometer, that means for a small change in delta P, if we want to have a substantial value of Y or readable value of Y, what we should do? We should make this part very small, so that even for a small delta P, we have a large Y. That means rho m minus rho W should be very small, nearly equal to 0, or rho m, that is the manometric fluid density, will be very close to the density of the working fluid. But in practice, it is very difficult to have a manometric fluid whose density is close to the working fluid and at the same time defining a meniscus, a good meniscus. That means a separation of surface between the two liquids has to be defined. So, well defined meniscus should be there, otherwise we cannot read Y. So, a well defined meniscus between the immiscible liquids and also a close density values are not practically feasible. So that without going for changing the properties of the liquid, we go for some other changes in the construction of the manometer to measure small pressure differences. This is one which is known as inverted tube. This is done inverted tube manometer, inverted tube manometer, inverted tube manometer. What is inverted tube manometer? In this case, what happens if we consider a horizontal pipe and the fluid is flowing through it? What do we do if we want to measure the pressure difference between 2 points A and B? So, inverted tube manometer is placed like that, that is in an inverted way. Sorry, that is. What happened is that there is a valve. Inverted tube manometer contains air as the working fluid, air as the manometric fluid, air as the manometric fluid with some pressure. So, pressure of the air is adjusted by the valve. That means, if you open the valve, some air may come out and you know the mass of the air is reduced, so pressure in the closed system of the air is reduced. So, this way we can change the pressure of the air inside it. So, what happened? The working fluid, depending upon the pressure, will go inside. For example, if the pressure PA is greater than PB, that will be adjusted. It is very simple. So, therefore, if we measure this height, let this side is y, then we can get simply the PA here is equal to some pressure, let air pressure is P0. So, P0 plus rho W into y, let this is x, rho W into G into x plus y. Similarly, here PB is equal to P0, the same air pressure in the closed system, the air will impress the same pressure and there is no difference in the pressure because of the height of the air. So, you can tell sir pressure here is P0, so here pressure will be P0 plus height of the air. So, that height of the air we neglect because the density of the air is so small compared to the working fluid. If this is a liquid, usually working fluid is a liquid, so that we neglect for small height the variation due to pressure because of the height of the air. So, the same P0 pressure is impressed here. So, P0 plus rho W G into x. So, if you just subtract one from other, you get PA minus PB is equal to what will be there? Rho W Gx will cancel, rho W G. That means there appears the density of the working liquid. So, therefore, by this we can have, so this is low compared to the manometric fluid. If you use a manometric fluid in a usual conventional U-tube manometer, so we can have a large deflection even for a small pressure difference. Okay. Then another modification is inclined tube manometer, inclined tube manometer, inclined tube manometer, inclined tube manometer, inclined tube manometer. What is it? It is very simple again on principle. If one limb of the U-tube is made inclined, what happens? If one limb of the U-tube is made inclined, just imagine what will happen. That means it is very simple to have an amplification. That means if a pressure is, that means it is connected to one pressure point, another pressure point. Let this is A, this is B with the working fluid. Then what will happen? The manometric fluid will be deflected like this. Okay. So, let us have the deflection like this. That means for a vertical deflection y, we can read this as, so this corresponds to, for example, this vertical deflection y corresponds to a deflection s along the pipe with a magnification that if this angle is theta, so s is equal to y by sin theta. That means if we measure the displacement of the mercury or the manometric liquid, usually mercury is used as manometric fluid or manometric liquid along the pipe, then that will be amplified by a factor of 1 by sin theta with a y. So, this y will be proportional to the pressure differences Pa and Pb applied here. So, the magnification is made by this inclination, so that this S, if we measure along the pipe, along the inclined tube of this U tube manometer, so we measure a greater displacement than the y because of this geometrical magnification 1 by sin theta. This is an inclined tube manometer. Usually we have to find out the difference of level, that means we will have to find out S from this when the pressure is applied. That means we will have to recognize the deflection here and the deflection here. But to avoid this, what is done, that one part is made with larger cross section compared to the other part. Why? In that case you will understand that only the movement of the liquid in one limb is sufficient to be read. That means let us consider a manometer like this, inclined tube manometer, where this part of the limb is made with a larger cross section, let A, and this part cross section is A, where A is very larger than A, greater than A. So pressure is being, this is connected to a system, this is connected to another system, Pa, Pb. Before the connection, let the level of the liquid was like this is the original level of the liquid, manometric liquid, there is manometric liquid. Now after the connection with the pressure where Pa is greater than Pb, then the manometric liquid will be depressed here. So manometric liquid will come here and it will go here like this. So now we will have to find out this deflection. If you write the manometric equation, you will see we require this deflection y to be measured. That means in that case we have to measure this S, try to understand this S. So this S to measure we will have to know this length, but we do not do that. What we do, this part we do not make transparent, only this part is made transparent. We see the initial level in the transparent inclined part, we see the final level. So instead of measuring this, we measure this S1. That means we neglect the measurement of this. Why we can neglect? How we can neglect? If this area is much larger than this, so this deflection, that means this vertical deflection is much smaller compared to this displacement in the tube from the continuity, because the same fluid which is depressed here will be going up in this tube as the cross sectional area is much larger. The cross sectional area is made 2 times in the order of magnitude, so 100 times larger than it. The diameter is made some 10 times more than these usual cases. So therefore this depression is much more negligible compared to this displacement. So that error in taking S1 as the measurement as instead of S is very less. So that we need only this inclined part of the tube to be transparent, and this can be made metallic if the cross sectional area is larger. So we simply what we do, we take the initial level and we take the final level, and this displacement along this inclined tube is measured. Okay. So this displacement is magnified by a factor of 1 by sin theta instead of having a vertical displacement here that we have explained, I have explained. Now here the one question comes, if the magnification factor is 1 by sin theta, we can go still lower and lower value of theta so that we can get more magnification, that for a small difference of delta y, very small difference in pressure or small difference in y, we get a larger value of S. So there should be a limit. Limit is like that, as you go on decreasing theta, you will see this meniscus, free surface of the manometric fluid will be so flat, it is very difficult to find out its exact position, whether we will take its end point, we will take its middle point or here. So this will cause error to the system, because free surface will be horizontal. So if we make a higher value of theta, this surface will be such that the difference in S, that means the distance along the length from these 2 points on the free surface will be less. So if you make more horizontal the surface, you see like this, then a free surface will be so wide because it has to be horizontal. So these 2 points, if you measure the displacement in this direction, this will cause a substantial error. So that theta should not be very low. Theta is usually restricted between 10 degrees. Okay, so this is the principle of inclined tube manometer. Now we will discuss the pressure. Now next section is the pressure exerted by a surface submerged in a expanse of static liquid, that is hydrostatic force exerted on surfaces submerged. So when a surface is submerged in a fluid or at rest, then the pressure will be exerted on the surface, and what should be the pressure exerted on a surface. Okay, so let us write that hydrostatic. Oh, this is already done. Let us see that hydrostatic force on a submerged surface. Hydrostatic force on a submerged surface. We should first consider plane surface. Now let us consider a fluid at rest with a free surface. Okay, let this is its free surface of the fluid. Now let consider this is a liquid and a surface is submerged in a liquid. Within the liquid, this is the surface at an inclination of theta. That means the plane of the surface and the plane of the free surface makes an angle theta. That means if we see the surface from this top view, so this is the surface of area A. That means surface is inclined surface. So this is the free surface, this is the surface which is inclined at an angle theta with the free surface. If you see from the top, so this is the view, so this is the surface, an arbitrary surface. Now you see, in this case what happens, you can argue that the pressure force is acting on both the sides of the surface due to the water, and they at any point they will be equal. The pressure on this surface and pressure on the other side will be equal. At this point also they will be equal. So the net resultant force will be 0. But this is not the case we are considering. In actual case, a surface submerged will not experience a net force. But we are interested to find out what is the force exerted on the surface if other side is exposed to atmosphere. That means what is the gauge pressure exerted or the gauge force exerted on this surface from one side. That means we will consider as if the other side is exposed to atmosphere, and what could be the net force exerted on this surface. You can just think the problem in that way. Otherwise you can argue, sir, in the actual case they balance each other. So we are not considering the forces from other sides, we are considering the forces from one side, other side is as if open to atmosphere. Now as you know, the pressure varies linearly with H in an incompressible fluid if it is a liquid. So therefore there will be a variation of pressure like this. That means the pressure force will act on the surface like this. The pressure force will act on the surface. Let this is the surface. Let AB is the surface. Pressure force, this is the pressure force. Will act because the pressure at any point is directly proportional to the height. Now let us consider an elemental area. Now first of all, before that, let us consider a coordinate axis. This point is the point, this is the line seen as a point where the plane of the surface and the free surface meets. The plane of the surface and free surface meets at a line which is seen at a point from this direction perpendicular to the plane of the paper. This is taken as the origin O. And OY, Y coordinate is taken a line along this plane, along the direction of the plane, and perpendicular to this OX axis is taken. I think there is no problem. Now let us consider a small elemental area dA which is at a depth H. That means this one is H. That means this elemental area here, which is seen as the area from this surface area dA, which is at a depth H from the free surface. So what is the force on this elemental area? First of all, what is the pressure exerted by the liquid on this elemental area? It is at a depth H from the free surface. Here we are considering the force or pressure above the atmospheric pressure. So this will be simply rho GH. Rho is the density of the liquid, rho. So rho GH. H is the depth at which this elemental area is considered. So therefore the force on this elemental area will be dF will be rho GH times dA. And this H from the simple geometry, if I define y as the coordinate, y coordinate of this elemental area from the x axis. So, this h will be simply y sin theta. So, it will be y sin theta. Well, so if we integrate this force over the entire area, that means double integration over the entire area, we will get, now rho is constant, g is constant, sin theta is constant. Why not we take out rho g sin theta? Oh sorry, I am sorry, h will not be there in this case, rho g h is y sin theta, rho g sin theta y dA. I think this is clear. Rho g h is the pressure here on this area. So, the force on the elemental area dF is rho g dA, that is the rho g h into dA. dA is multiplied because the pressure into area is the force, and h is substituted as y sin theta. This is theta, this is y, this is h, so y sin theta. So, this becomes rho g sin theta y dA if you make a double integral over the area A. So, this is rho g sin theta y dA. Now, what is this term? This term has an implication. You see that y dA over the entire area represents the, what is this? Moment of the area about x axis. So, this term is the y dA, this term is the moment of the area about the x axis. So, now if we define a center of area, you know what is center of area very well. So, if you define C as the center of area, whose y coordinate from the reference x axis, if it is yc, then by definition yc is what? The moment, first moment of area over the area A divided by the total area dA. That means the total area A. That means y dA is equal to yc into A. So, if we replace this here, we get a very interesting result that F becomes is equal to rho g yc into A instead of integral y dA. That means rho g yc sin theta into A. And what is yc sin theta? Yc sin theta is similarly the vertical depth from the free surface. So, this is yc sin theta, and if I denote this as hc, that means where hc represents the vertical depth of the center of area. That means if it is yc, so yc sin theta is this vertical depth. That means if the center of area is at a vertical depth from the free surface hc, F is equal to rho g hc. So, this is a very interesting result. That means if there is a inclined surface, there is an inclined surface where we see the pressures at each and every point is varying because of their depth from the free surface, the total pressure due to this, total force due to this hydrostatic pressure is simply the pressure at the centroid. If one can find out what is the pressure value at the centroid times the total area will give you the force. That means it can be equivalently told that if this surface AB could have been placed horizontally, sorry, I am wrong. So, this will be at this, I am sorry. So, if this surface AB, this is wrong, surface AB could have been placed horizontally at a depth hc below the free surface, then what could have happened? The uniform pressure. In a horizontal surface, pressure at each point is uniform. This is the pressure P. Okay. So, this P is equal to rho g hc because of this depth. That means placing an inclined surface in a fluid, submerged in a fluid, is equivalent to place the same surface at the depth of its center of area. That means if we know the center of area, depth at the center of area, we can find out the pressure, and times the area is the total force. That means it is equivalent to it will experience the same force, rather we say it experience the same force if it could have been placed in a horizontal position at a depth hc, which is the depth at which the center of area of this area lies. Okay. So, this is one important conclusion. Now, next is to find out the point of application of this force. Now, it is true that the point of application of this force, well, I can put it here. Here itself you can see the point. How do I find out the point of? Now you see that the resultant force magnitude is known. That is equal to rho g hc into A. So if I know the value of hc, the centroid depth of the centroid from the free surface, I can find out the total force. And the direction of the force is always known, that it is perpendicular, because for all elemental surface the pressure force is perpendicular to the surface. Since it is a plane surface, the perpendicular at all points are parallel. So a scalar summation will do, so that the direction will not change, direction is perpendicular to the surface. But where is the point of application? It is also very simple. The point of application definitely will not coincide with the center of area. Why? This is because the forces are not proportional to the area. As we go along the surface, you see the depth is increasing. So even for the same area here, if we have another same area here, the two pressure forces and the two areas are not same, because the pressure intensity is changing because of the depth. So it is common sense that as we go below the surface, free surface, the pressure is more and more. So therefore the center of pressure will lie, for example here if we denote this Cp as the center of pressure, which will lie beyond C, center of area, towards the depth of the fluid. So let us consider this is the center of pressure, and let us define the coordinate of the center of pressure as yp from the x axis, and let us define this as the xp from the y axis. Now common sense will tell us to make the Cp here, not here. Cp would have coincided with C, the center of area of the forces could have been proportional to the area element, but it is not so. Since the pressure is increasing, that means with the depth, that means the lower portion of the area is having more force, so that it will be this side from the center of area. Now if we apply simple mathematics to find out the yp and xp, that what is that? That means the resultant force multiplied with yp will be the sum of the moment of the component forces about the OX axis. Alright, that means if I write this, F into yp will be the sum of the moment, that means integral of the component forces, moment of the component forces on the x axis. What is this component force? Rho g dA y sin theta, and its moment will be about y axis, x axis is another y. That means it will be simply rho g y square sin theta dA. Okay, rho g y square sin theta dA. That means yp will be integral rho g y square sin theta dA divided by f. F is rho g y sin theta dA. That means it is integral rho g sin theta y dA. So this is already found as integral y dA as hc into A. So therefore I write is at hc into A, and here I will write as integral y square, sin theta will cancel, y square dA, y square dA into hc by A. What is y square dA in this case? Y square dA, you see, is the second moment of area of the surface about the x axis. Well, very good. Second moment about x axis. Sometimes it is second moment of area or moment of inertia of the area about this x axis. Alright. So Ixx divided by hc into A. Alright. Is there any problem? No problem. Okay. Now what we get, what we do, that this can be replaced by a parallel axis theorem, but before that let me do the x one. So what will be the x component? Now x component, if xp we want to find out, we can take the moment in the similar way about the y axis. That means this will be simply integral of rho g x y sin theta dA, all right, divided by what is this thing? This is rho g sin theta y dA. All right. Now, if we come here, we see that this becomes xp is equal to integral x y dA divided by what is that? This we can write as hc into A. So therefore we see that this is known as the product of area I x y. What is this x y dA? That is product of area. That is known as product of area. That means if this be the area, this x coordinate of at any point or at any elemental area, this has the y coordinate. So the integration of x y dA over the entire area is known as the product of area, and I just simply write it as x y. This already you know, hc into A. So we know xp. All right. Okay. Now by a parallel axis theorem, now if you know any question, please you can ask at this moment. So before we proceed to the next one, this is all right? Okay. Is there any problem? Please. Huh? This will be yc, no? Oh yes, I am sorry, this will be yc. This will be yc. I am sorry. Because sin theta I am cancelling, this will be yc. Very good. Appreciated. Because sin theta I am cancelling from both these sides, numerator and denominator, so that I cannot take y sin theta as hc, convert. So it will be yc. Very good. Because sin theta as such is cancelling from the numerator and denominator. It should be yc. I think there is no other problem. Okay, all right. Now by a parallel axis theorem, you know that if I define the moment of inertia, that means if I take the parallel shifting of the axis as you have read earlier, and if I define x dash and y dash are the coordinate axis parallel to x and y through the centroid C, and if I now define, you understand this, x dash and y dash through the centroid C, and if I define now that Ix dash is the second moment of area or moment of inertia about Ox dash axis, then the relationship between this and the moment of inertia of the old x dash is Ix plus A into Yc square. That means the moment of inertia about this axis is the moment of inertia or the second moment of area about this axis plus area into Yc square. That is the distance of this axis from the earlier axis, Yc square. Similarly, well, all right. Similarly, for the product of area, if I define with respect to new x dash y dash axis, this will bear the relationship Ixy plus A. The two coordinate will come which will define the coordinate of the new axis from the old one. That means this is Yc, and in that case this is Xc. In our case, our new axis is to center of area. In that case, Yc, Xc are the y and x coordinates of the center of area. All right. Okay. So now if you substitute, you see the interesting results come. Yp is equal to, if I substitute this here, that means Ix. Okay. I am sorry, it will be minus. Ix will be Ix dash plus this. This will be minus. I am sorry. So Ix will be Ix dash plus this. Ixy, that means in the old coordinate will be in the new coordinate plus this. So if I substitute here, so what I will get? I will get Ix dash divided by Yca plus cancels Yc. So I get Yp minus Yc is Ix dash divided by Yc into A. Similarly, if I substitute this one here, what I will get? This is Ixy, Ix dash y dash. So we will get xp minus xc is Ix dash y dash divided by yca plus what we will get? Xc yc. That means if I substitute here, yc will cancel, a simply xc has come here. There nothing will be there. So I get this and this one. Okay, so therefore we see that yp minus yc is this one, and this is a positive quantity because Ix dash, it contains an integral with the square of the ordinate. So therefore the second moment of area is always a positive quantity. So yp minus yc is greater than 0. That means this quantity gives you the displacement in this direction. This is yp minus yc. Sometimes this is told as the eccentricity. That means how far the center of pressure is shifted from center of area in the direction along the plane. So this is yp minus yc. So this distance is given by a simple expression Ix dash divided by yca. Ix dash is the second moment of area about this Ox dash axis, and yc is the center of area in respect to this coordinate, and A is the area. But the most interesting fact is that xp minus xc becomes 0 because the product of area about the centroidal axis is 0, which means that xp is equal to xc. Because if I take the axis x dash y dash to centroidal plane, so the product of area is 0. So therefore xp minus xc is 0. This one can make from a common sense that if this C is the center of area, so whatever may be the arbitrary area, so the center of pressure cannot be shifted in a direction perpendicular to the plane, because any area in this side and another area will be always at the same depth. So therefore the pressure forces are proportional to the area element only. So therefore the center of pressure and center of area is not displaced in a direction perpendicular to the direction of the plane. So it cannot be disturbed. So therefore this is xp minus xc, that means this is the xp and this is the xp. So x coordinate of the center of pressure coincide, while the y coordinate, that means along the plane, is shifted towards the depth of the fluid by the amount which is given by yp minus yc is this. Okay, all right, you have understood this. This is the plane figure. So plane surface. So next class we will discuss the pressure forces on curved surface. Okay, thank you. Good afternoon. I welcome you all to this session of fluid mechanics. Last class we were discussing the force, hydrostatic force exerted on a plane surface submerged in a static expanse of fluid. And what we have finally concluded, that if there is a free surface of fluid and a plane surface, plane inclined surface is submerged in this expanse of fluid, then the pressure forces is exerted perpendicular to the plane surface at each and every point. Okay? And the pressure intensity at any point, as we know, that it is equal to rho times g times the height of that point or the depression of that point, that is the vertical depth of that point from the free surface. So the pressure intensity varies at different points depending upon their depression from the free surface. And finally we recognize that the total hydrostatic force due to these hydrostatic pressures on any one side of the plane surface is equal to the pressure intensity at the center of area of the surface times the total area. That means it is equivalently at the same area, if it is placed horizontally at a depth equal to the depth of the center of area of the inclined surface, then the pressure which could have been exerted, that is the uniform pressure, equal to rho times g times the height from the free surface, that is the height of the centroid for the inclined surface. So therefore we are concluded that for any inclined surface, the total pressure force is equal to the area of the surface times the pressure intensity at the centroid of the area or center of area. And we also recognized another fact that the pressure center, that is the point of action of these resultant pressure forces, passes through a point which is below the center of area, that means it is more at a more depth than that of the center of area, which is obvious because pressures are increasing with the depth, and the center of pressure can be found out by a simple expression that the moment of area about an axis which we take as the intersection of the plane surface with the free surface, we take an axis perpendicular to this. So, moment of area of this surface about this axis divided by the area and the coordinates of the center of pressure. So, this we recognize in the last class. Now, today we will be discussing the hydrostatic pressure forces or hydrostatic forces on submerged curved surface. If the surface is curved, then how we will find out the hydrostatic pressure force. Now, let us see in general here, let us first write hydrostatic force on curved surface, on a curved surface. Well, now let us see here in general a curved surface. So, this is a curved surface, you can see, which in general has got curvature in both the directions. So, a general curved surface which has got curvature in both the direction, it is immersed in a fluid whose free surface is this one, in an expanse of fluid. Now, in this case we consider a three-dimensional system because of this curvature in two directions. We consider the axis OX, OY at the free surface, that means this XY plane, coordinate plane is at the free surface, and OZ axis we considered vertically downward. Now, it is true that at each and every point on the surface the pressure force intensity or the magnitude is equal to rho times the density of the fluid, which is constant in case of liquid, times the g times its vertical depth from the free surface, which we denote by the z coordinate, that means rho g z. But the difference between this with that of a plane surface is that each and every point the force is normal to the surface which are not parallel. In a case of a plane surface, what happened? That force at, for example, if there could have been a plane surface, the force on each elemental area is normal to the surface and they are parallel to each other. So, therefore, a scalar summation of the elemental force was possible, which we did by simple integration of an elemental force throughout the area. But in case of a curved surface, since the normal at each end point of the surface, which is the direction of the pressure forces, changes because of the curvature, a simple scalar summation, that means a simple integration, will not be possible. So, therefore, the general procedure of mechanics, simple basic mechanics, is that in that case we will have to take an elemental force and we will have to fix certain reference coordinate directions in which we will take the components and sum up the components in a particular directions. Okay? And we will find out the components of the resultant forces in those directions and then again vectorially sum up the components to find out the resultant force. It is as simple as like this from elementary mechanics. So, now we concentrate here, we see to do that we recognize an elemental area dA which is at a vertical depth z. We just project this area here and this is shown here, that is the z in the yz plane. So, z represents the vertical height or depression from the free surface dA, from the free surface of this area dA. Now, you see the hydrostatic force due to pressure is acting on this surface. If we consider the force acting by the liquid on this side, I have told only one side we will consider, other side we will consider as if open to atmosphere, then this pressure force is normal to this area dF. Now, this force can be resolved into three directions with respect to this frame of reference OX, OY and OZ. Accordingly, dFx is the x direction, x component, dFy is the y component and dFj is the z component. Now, if we assume that the normal to this surface makes an angle alpha with the x coordinates, makes an angle beta, let this is beta, this big angle with the y, sorry, not this one, I am sorry, that means this one, not this one, this we make this normal to this with y axis is beta and normal to this with z axis, that means this angle as gamma. That means alpha, beta and gamma are the angles made by the normal to this area with x axis, with y axis, that means this angle, and with z axis. Then we can tell simply that dfx is equal to what? dfx is equal to df. Now df is dA into rho g z if we consider that this area is at a vertical depth z from the free surface. So simply rho g z times what we can write? dA cos alpha. Very good. What is dfy? Rho g z dA cos beta, and what is dfz? That is rho g z dA cos gamma. Now you see this dA cos alpha physically represents the projected area of dA on yz plane, that we denote as dAx. That means it is the projected area of elemental area dA on a plane whose perpendicular is x, that means on yz plane. So therefore we can replace dA cos alpha by dAx and we can write dfx is equal to rho gz dAx. Similarly, we can write dfy as rho gz. Similarly, A cos beta will be the projected area of dA on a plane whose perpendicular is the y direction, that means it is on the plane xz. So that we represent as dAy. And similarly, dfz will represent rho gz times dA cos gamma, which is the projected area of dA on a xy plane. That means the plane perpendicular to z direction, which is shown here. This area is dAz. dAy area is not shown here, is difficult to show in this two-dimensional paper. Now you see that if we now integrate, now the different direction component forces of this elementary force F is made. Now we can make a scalar sum. That means now we can tell Fx as integration of dfx double integration, because this is equal to rho g z dx. So therefore you see rho g z dx, now you can recall this can be simply written considering a force on a plane surface, that this is rho g zc into ax. Rho g is common. If you take rho g out, then the double integral z dx is made over the entire area ax, where ax represents the projectional area of this entire curved surface area A. That means it is the projectional area on yz plane, that is the plane perpendicular to x axis of the entire curved surface area ax, and zc represents the center of area of that projectional area. Okay, or you can tell the projection of the center of area on the curved surface on yz plane, both are same. So therefore we see simply Fx is equal to, again I am writing, is very interesting result, rho g zc ax. In a similar fashion, I can write Fy by integrating this dfy as rho gz, okay, day double integration, which becomes is equal to rho gz c, rho gzc into ay, where zc is again the center of area, the vertical distance or the coordinate of the center of area projected on xz plane, and ay is the projected area of the entire area or entire curved surface on the xz plane, that is the plane perpendicular to y. And similarly, we can write dfz is equal to integration of rho g j dAz. Now here we stop, we cannot write anything more for here. Now two very interesting result now comes out from this expression for Fx and this expression for Fy. Now we see therefore the x component of the hydrostatic force on the entire area is equivalent to the hydrostatic force on a vertical surface, vertical plane surface which is parallel to yz plane, and area of the surface equals to the projected area of this curved surface on the yz plane. Similarly, the y component of force on this curved surface is equal to the hydrostatic force of a plane surface area which is parallel to xz plane, and whose area is equal to the projectional area of the surface on xz plane. Therefore, we can conclude from here that the hydrostatic force in any horizontal direction, the hydrostatic force in any horizontal direction of a curved surface equals to the hydrostatic force exerted on a plane surface which is perpendicular to that direction and whose area is equal to the projected area of the plane on that particular plane perpendicular to this direction. So again I am telling, the conclusion is like that, if there is a curved surface, sometimes it helps us in solving problems, that if there is a curved surface submerged in a liquid, then the hydrostatic pressure force in any horizontal direction, it may be x, it may be y, any way you can orient in any horizontal direction, is equal to the force on a plane surface whose area is equal to the projected area of that surface in a plane perpendicular to the direction. That means if we consider a plane perpendicular to the direction, the horizontal direction in which we are finding out the net component of the total hydrostatic pressure force on the curved surface, then if we imagine a plane perpendicular to that direction, then this is equal to the hydrostatic pressure force on a plane surface which is the projection of this curved surface on that plane which is perpendicular to that horizontal direction. So this is a very important conclusions we get.